Welcome back. In this lecture we're going to be looking at how data is managed in SYCL applications. In this lecture we're going to cover the SYCL memory model, how to use buffers and accessors to manage data dependencies, how to access memory in different memory spaces, the different ways to access the data, how data dependencies can be used to control the execution order of your kernels, and finally how to synchronize data. First up, we're going to cover the SYCL memory model. In the last lecture we looked at the SYCL execution model and the composition of work items and workgroups. Here we're going to see how this relates to the hierarchy of different memory spaces available in SYCL devices. The fundamental component of execution was the work item, a single thread of execution. Now each work item can access a dedicated region of memory called private memory, and no work item can access the private memory of any other work item. Next up we had workgroups, a group of work items collected together. Each work item can also access a dedicated region of memory called local memory. Local memory is accessible to all work items of a workgroup. This makes it very useful for sharing partial results between work items. Again though, no work item can access the local memory of another workgroup to its own. Finally we had the ND range. Each work item can also access a single region of memory called global memory. Global memory is accessible to all work items in the ND range. It is also the only way to communicate data in and out of kernels, except for constants. Each work item can also access a region of global memory that is reserved as read-only called constant memory. Using constant memory can be an optimization for applications as it doesn't require cache since it's read-only. However, not all implementations provide a benefit from using this. Each memory region, private, local, and global, has a different size and access latency. Private memory is the smallest, with local memory being larger and global memory being much larger still. And with global memory being the slowest to access, as it's often accessed across an off-chip connection, and local memory generally being quite a bit faster, as it's usually on-chip, and private memory being faster still. Now that we've covered the memory model, we're going to take a look at how SYCL manages data using buffers and accessors. In SYCL, the storage and access of data is separated into buffers and accessors respectively. A buffer manages the data across the host application and one or more device, with the latest modified copy of the data being available in one of these locations at any given time. An accessor represents a request to access data on a particular device, in a particular memory space and for a particular kernel function. As well as describing requirements to access data, accessors are captured or stored in a kernel function and used to access the data once in the kernel. In order to achieve this, the host compiler and device compiler interpret accessors slightly differently. The host compiler interprets accessors as host application objects used to describe data dependencies to the runtime. And the device compiler interprets accessors as a wrapper over a pointer to the data that can be used very much like a regular pointer to access the data once in the kernel. There are many ways to construct a buffer that give you a range of options for managing data. Here we're going to focus on the most common of those. A buffer can be constructed with a pointer to host memory, i.e. memory allocated on the host application. For the lifetime of the buffer, this memory is managed by the buffer. So this means that modifying the original data on the host is undefined behavior, as the runtime needs to be able to freely move it between the host application and any devices that are accessing it. One important thing to note is that buffers are lazy. They won't allocate memory or copy anywhere until they're told to. This will only happen when the runtime knows where the buffer needs to be accessed. This is done by constructing an accessor to that buffer. There are a range of different types of accessors and ways to construct them. We're going to cover some of these later in this lecture. When an accessor is constructed, it is registered with a command group via the handler object. This connects the buffer being accessed to the way in which it's being accessed and where it's to be accessed. With this information, the runtime can schedule the command group in relation to others. Once the runtime scheduler selects that command group to execute, it must first satisfy its data dependencies. This usually means copying the data to the target device. However, if the latest modified copy of the data is already on the target device, it doesn't need to move. Sometimes the dependencies are on data already being written to by another kernel. In this case, it must wait for that kernel to complete before copying. Remember I said that buffers are lazy. so data will remain on a device even after the kernel is completed until it's requested elsewhere, or when a buffer is destroyed. When this happens, the buffer destructor will wait for the latest modified copy of the data to be copied back to the original pointer on the host application. Now we're going to look at a couple of different cases of using a buffer across different devices. If a buffer is accessed on one device and the latest modified copy of the data is on another device, then the data will be copied over. Now if the two devices are in the same context, for example both Intel, then the data will be copied directly from one to the other. However, if the devices are from different contexts, then the data will be copied via the host application. It's important to consider this as it could incur further overhead when copying between devices. Now we're going to take a look at the different kinds of accessors and how to use them. The accessor class has a number of template parameters which govern the various properties of how it accesses data. Firstly, there's the element type. This is the data type of the elements that are being accessed. This can be any standard layer and trivially copyable type. Next there is the dimensionality, which can be 1, 2, 3, and even 0. Zero-dimensional accessors are a special case for accessing a single scalar value. Then there is the access mode, which is used to describe whether the accessor is reading and writing to the data. There are also discard variants of these, which describe an anti-dependency, explicitly specifying that the original data can be discarded. Next there is the access targets, which specify the memory space that the memory is going to be accessed in. There are additional access targets for images that I've not described here, but I won't be covering these in this lecture. Finally, there is the placeholder parameter. This is an optional mode which allows certain accessors to be constructed outside of a command group and registered later. Let's look a bit closer at the access targets. Accessors with the access targets global buffer or constant buffer will allocate memory and copy to the global and constant memory spaces respectively. Accessors with these access targets must be constructed from a buffer. A useful shortcut for constructing a global or constant buffer accessor is provided by the getAccessMember function of the buffer class. The element type and dimensionality must always be the same as the buffer. Next, let's take a look at the access target host buffer. This provides immediate access to the data in the host application, so this means it must be constructed outside of a command group. Again, a shortcut to constructing a host buffer accessor is provided by the buffer class. Constructing a host buffer accessor can trigger synchronization and copy the latest modified copy of the data back to the host application. Also note that a host buffer accessor will block any other accessor from accessing the data until it's destroyed. Lastly, we have the local access target. Local accessors are a special case because they are not constructed from a buffer. Instead, you simply specify the type and the range of elements you want to allocate. However, local accessors allocate memory per workgroup, as they allocate memory in the local memory space. Local accessors are also only available for the duration of a kernel function. Now let's take a closer look at the access modes. The various access modes can be broken down into three main components. An access mode with read creates an accessor with read access to the data. An access mode with write creates an accessor with write access to the data. And this creates a dependency on any future accessor which accesses the same data. An access mode with discard creates an accessor that will discard the previous value of the data. This breaks a dependency on an accessor which are writing to the same data. Next, we're going to take a look at accessor resolution. If a command group has more than one accessor to the same data with conflicting access modes, they need to be resolved into one access mode in order to determine what the dependency is. The rules are, if you have both a read component and a write component, the result is the sum of those, so it will be a read-write access mode. Also, if you have an access mode with the discard component and one without, the result is one without, as that's the stronger guarantee. Within the kernel function you still have multiple accessors, but the runtime dependency is resolved and the accessor is aliased to the same data. Here we have an example of this. We have two accessors here, in A and in B, which both access the same buffer, buff I. One is read and one is write. Both will point to a single allocation of global memory, but the command group will resolve these two accessors into a single dependency of read-write. Finally, we're going to take a look at ways in which you can access data either in a kernel or on the host application using accessors. There are a few different ways that you can access the data as represented by an accessor. Firstly, the subscript operator takes an ID. For dimensions larger than 1, the index is linearized using row major ordering. You can also use nested subscript operators when there's more than one dimension, so you have one subscript operator for each dimension. Finally, you can also retrieve a pointer to the underlying memory by calling getPointer. This returns an object of multipointer, which is a pointer wrapper class which knows the memory space the data is in. Here we have an example of using the subscript operator of the accessors to access elements of the memory, passing in an ID. Here we have another example doing the equivalent, but by retrieving the multipointer for each of the accessors and using the subscript operator on the multipointers to access the elements in memory. Here we use the ID's member function getLinearID to retrieve the linearized ID. Again, this is in row major ordering, just like the subscript operator of the accessor. So this concludes the lecture on managing data in SYCL. There should now be some time for us to answer any questions you may have on this.